This brings us to Module 4, Reference 400. The first topic in this module is of utmost importance to you as a student of chemistry, and that is the topic of chemical kinetics, reference number 401 in your workbook. Chemical kinetics is that branch of chemistry concerned with the speeds or the rates of chemical reactions that can range from extremely rapid, like acid-base reactions, which occur in microseconds, to reactions that are extremely slow, like the geological processes that can take millions of years to complete. Experimental evidence has been gathered on reactions that occur at rates between these extremes. Chemical kinetics is a study of the factors influencing the rates of the chemical reactions in the various steps that make up the so-called reaction mechanism that add up to the overall reaction, describing the conversion of reactants to products. A thorough understanding of the ways in which these factors can influence the rates of reactions is of utmost importance to chemical engineers because they are responsible for controlling the reactions in industry, where we look for the highest efficiency and productivity. Although, in some cases, chemists try to slow down reactions like rusting of iron, in most cases, they apply the principles of chemical kinetics to obtain the highest possible yield of the desired product in the shortest possible time. How do we now measure the rate of a chemical reaction? Let us look at the reaction between two imaginary diatomic molecules, A2 and B2, to produce the product molecules AB. The rate of a chemical reaction can be measured in terms of the rate at which the reactants are being used up or the rate at which products are formed. In other words, it can be given by the decrease in concentration in mole per decimeter cubed of a reactant per second, or by the increase in concentration in mole per decimeter cubed of a given product per second. This curve shows how the concentration of reactant A diminishes with time as it is used up, while this curve shows how the concentration of product AB increases with time as more and more of molecules AB are formed. We notice that the rate is given by the gradient of the concentration versus time curve. Rates of reactions are not constant, but they change with time. As you can see the gradient changing here. This is because the concentrations of the reactants decrease with time, while those of the products increase with time. The smaller the concentration of the reactants, the slower the reaction will be. The instantaneous rate of a reaction at a given point in time is always given by the gradient of the tangent at that point on the curve. So the rate of consumption of reactant A2 at time point T1 is given by delta A2 divided by delta T1. In order to always obtain a positive value for the rate of reaction, we use a negative sign for the rate of consumption of any reactant. Many of the observed facts of reaction kinetics have been interpreted in terms of the collision theory. In your workbook, reference number 401.2. Now, what are the basic assumptions of this very important theory? When the atoms, molecules or ions of two reactants A and B are placed in the same reaction container, the product C and D can only form after collision between the reactant particles A and B. Now, if every collision between the reactant particles was effective, in other words, if it leads to products, then all chemical reactions would be over in a very, very short period of time. They would be almost instantaneous because of the vast number of collisions per second.
But sir, why is only a small percentage of collisions effective?
When the particles approach each other for collision, the electron clouds or orbitals will come in contact first, so that if the total kinetic energy of the two approaching particles is too low, then the repulsion between the electron clouds will simply cause the particles to fly apart without forming the products, and they will have the same kinetic energy.
But sir, will they ever react if repulsion causes them to fly apart after collision?
Yes, if the combined kinetic energy of the two approaching particles is large enough for the electron clouds' repulsion to be overcome, then these electron clouds will overlap, causing a rearrangement of the electron structures, which can lead to the breaking of existing bonds of the reactants, and at the same time, formation of new bonds in the products. The activation energy is the minimum kinetic energy that the particles of the reactants must have in order to collide and to produce the so-called activated complex, in which the bonds in the reactants are beginning to break, while at the same time, new bonds in the products are beginning to form. In other words, to react to produce the final products. Some substances react spontaneously. For example, the neutralization of acids by alkalis or the spontaneous combustion of phosphorus. For the applicable demonstrations, you can refer to the part 1 on chemistry, reference numbers 207.1 and 104.5. Most reactions, however, require some energy in the form of heat or heat through friction or a spark or light or other form of energy in order to initiate the reaction. But after initiation, the reaction will run spontaneously. Ammonium dichromate will not decompose unless we first activate the reaction. In this case, we're going to initiate the reaction with a red-hot wire. We dim the light for a better effect. You know, I want to give you one more warning. Never ever try to do experiments on your own. Always do experiments under the close supervision of your teacher, or leave it altogether. Some reactions require extremely small activation energies. For example, the decomposition of nitrogen triiodide. In this case, I'm going to initiate the reaction with a mere touch of a feather. Let us look at an example of the application of the collision theory by considering the collision between two imaginary gaseous diatomic molecules, one consisting of two atoms of the imaginary element A and the other of two atoms of the imaginary element B, to produce two imaginary gaseous molecules AB and AB. With end-on collision, the activated complex cannot decompose to form the products AB, since the outer A atom and B atom are not in close contact to produce electron rearrangement, and the initial reactants are simply regenerated when they fly apart with the same total kinetic energy as before the collision.
So if they don't react with an end-on collision, how must they collide to react?
Here, perhaps you can show us.
Okay, well, they don't react like this. So I guess, Stephen, they must react like this.
Exactly, Era. We call that a broadwise collision, where the reactants collide and we have close contact between both A and B particles at the ends of the molecules. And this will produce the activated complex that can decompose to form the final products that will fly apart. So what happens is that the initial covalent bond between the atoms of element A and between the atoms of element B are finally completely broken, while the new covalent bonds between the particles of elements A and B are finally completely formed in the products. To summarize the collision theory, we can say that, in the first place, the particles of the reactants must collide before products can form. In the second place, the rate of any reaction is always directly proportional to the number of collisions between the reactant particles per second. This is the same as saying that the rate is directly proportional to the number of particles of reactants A2 and B2 colliding per second, which in turn is directly proportional to the product of the concentrations in mole per decimeter cubed of the reactant particles A2 and B2. Only those collisions for which the combined kinetic energy is greater than or equal to the activation energy will collide to form activated complexes that can decompose to form products. Here, can you tell me why you think that even in many reactions when the kinetic energy is sufficient, in other words, greater than or equal to activation energy, we still don't get products formed? I'll give you this diagram as a clue.
What did you say, Stephen? Well, I can see here that they have to react broadwise.
Is that they have to collide in the right way?
Exactly, Stephen. For the collisions to be efficient, the colliding particles must have the correct orientation. So, we can say that the rate of a reaction is directly proportional to the number of collisions between the reactant particles per second. But you know, not all collisions are effective. So we must multiply these collisions by second by a fraction. What fraction? The fraction of collisions with sufficient kinetic energy. But not even all these collisions are effective. So we have to multiply by a second fraction. The fraction of collisions with a correct orientation. We can change this proportionality into a useful equation by introducing a constant of proportionality. In this case, the constant of proportionality is called the specific rate constant, which is a reflection of the fraction of effective collisions of the reaction. For every temperature, a given reaction has a different rate constant.
So why is the rate constant determined by the temperature?
Well, here you see the temperature is always directly proportional to the average kinetic energy of the particles. So if the temperature is high, the value of the kinetic energy will be high, and so will the rate constant be, and the reaction will be fast. On the other hand, if the temperature is low, the kinetic energy will be low, and the rate constant will be low, which means the reaction will be slow. Stephen, what is the meaning of rate constant then?
That's how fast the reaction takes place.
Excellent, Stephen, you understood very well. To understand reaction kinetics, we need to know the types of changes that colliding reactions can undergo as far as energy is concerned. For the changes of the energy during chemical reactions, refer to reference number 401.3 in your workbook. Stephen, can you still remember the two types of reactions one can have as far as energy changes are concerned?
I think so. So is that the exothermic and endothermic reactions?
That's right, Stephen. You know, in an exothermic reaction, heat is always liberated during the reaction, whereas in an endothermic reaction, heat is always absorbed. Now, Stephen and I are going to do a few demonstrations of exothermic reactions. Stephen, just open the gas for us. Okay, I'm going to ignite it for you here. Just hold a piece of magnesium ribbon in the flame.
Is that to activate it?
That's right.
Oh, there, it's activated. Just look at all that heat.
The dilution of acids is a highly exothermic process. Let's see what happens if I add this concentrated sulfuric acid to the water in this beaker. Just watch how the temperature is rising over here. In this porcelain dish over here, I have a mixture of copper 2 chloride and common cane sugar. I'm going to add some potassium chloride to the mixture here and mix it. Then make a pile of the mixture on this tile and a little dent. I add concentrated sulfuric acid to activate this reaction. After an incubation period of a minute or two, we have a highly exothermic oxidation reaction. With strontium chloride, instead of copper chloride, we get the following exothermic oxidation. I am mixing sulfur and zinc dust in this porcelain dish here. And we make a little pile on the tile here. In this case, we activate the reaction with a red hot wire. The products of this exothermic reaction are zinc sulfide, zinc oxide, and sulfur dioxide gas. Let's now look at two examples of endothermic reactions. We first place a few drops of water on this wooden base, and then I place a beaker containing ammonium nitrate on top of the water and add to the beaker 50 milliliters of water to try and dissolve this ammonium nitrate. Now this is an endothermic solution process. What does that mean? It means the temperature of the solution will drop. It will cool down. Let's try and dissolve it. Let's measure the drop in temperature in this solution. Just follow it there. The drop in temperature was sufficient to freeze the beaker to the block, as you can see. Our second example of an endothermic reaction is the thermal decomposition of potassium chlorate. I have it in the test tube here. This reaction has a very high activation energy. First we melt the potassium chlorate, and then at about 400 degrees Celsius, the oxygen only starts forming. The potassium chloride is only beginning to melt now. The reaction is underway, as you can see the oxygen produced over here, and we collect it in the cylinder by downward displacement of water. Watch what happens if I remove the flame. Can you see how the reaction slows down? And eventually it stops completely. Because in the case of an endothermic reaction, we can only sustain the reaction if we continually add energy to the reaction mixture. Now that you understand the difference between exothermic and endothermic reactions, it's time for us to look at the potential energy curve for a very, very important exothermic reaction, the well-known water-gas shift reaction.
Sir, please can you tell me what the water shift reaction is all about?
Here, the water-gas shift reaction is a vital step in the Fischer-Tropsch process used by Sasol to produce hydrocarbons like petrol and other useful compounds. On the vertical axis, we plot the potential energy of the system, and on the horizontal axis, we plot the reaction coordinate, which tells us how far the reaction has proceeded from the initial reactants, carbon monoxide gas and water in the gaseous phase, to the final products, carbon dioxide gas and hydrogen gas. Initially, when the reactant particles, carbon monoxide gas and water in the gaseous phase are far apart, the potential energy of the system is simply the sum of the individual potential energies of carbon monoxide and water by itself.
Sir, how can the potential energy of the reactants be zero? Haven't they got any potential energy?
Potential energy is relative. It makes no difference what the actual values are. For purposes of comparison, we assign a value of 0 joules to the potential energy of the reactants. Potential energies above the 0 level are taken as positive, and below this level are taken as negative. Therefore, if the potential energy of the system increases, the curve will rise above the 0 level, as you can see for this portion here. And if the system undergoes a net decrease in potential energy, the curve will drop below the 0 level, as you can see for this part of the graph. When the reactant particles, carbon monoxide gas and water in the gaseous phase approach each other for collision, we illustrate the approach over here, then work must be done because of the forces of repulsion that we have between the electron clouds over here. This means that some of the combined kinetic energy of the colliding particles is converted to potential energy of the system, and the potential energy of the combination of colliding molecules will increase to a maximum when the activated complex has formed.
Yes, sir, okay, but can you please tell me again what an activated complex is?
Okay, Era, let's try. The activated complex is a transition state between the reactants and our final products. In the activated complex, some of the bonds in our reactants, like the bonds between hydrogen and oxygen in water here, are lengthened and are partially broken, while at the same time, the new bonds, like this one here between the hydrogen atoms, are partially formed, and also in the carbon dioxide. Can you see those bonds there? They are partially formed. Can you still remember the main condition from the collision theory for reactions to take place?
Yes, I think so, sir. Reactant particles must have enough kinetic energy before collision.
That's right. Only those collisions with the correct orientation for which the total kinetic energy of the colliding particles is greater than or equal to the activation energy can produce activated complexes. And these activated complexes can decompose to produce the final products, carbon dioxide gas and hydrogen gas. This happens when the existing bonds between the oxygen and hydrogen atoms are completely broken, and the new bonds between the hydrogen atoms and the carbon and oxygen atoms are completely formed. For an exothermic reaction, the total drop in the potential energy during the decomposition of the activated complex into products is greater than the activation energy by that much. This drop in potential energy is converted into the kinetic energy of the product particles flying apart. This means that the system will heat up and give out heat to the surroundings. In this case, 41 kilojoules for every 1 mole of carbon dioxide gas and 1 mole of hydrogen gas formed. We call this the heat of reaction delta H. Since the average kinetic energy of the products will be greater than the average kinetic energy of the reactants, the temperature of the system will rise, since temperature is always directly proportional to the average kinetic energy of the particles of the system.
Sir, if we come across an equation, how will we know that the reaction is exothermic?
There are two ways of writing exothermic reactions. We can either show the heat developed as one of the products, or we can simply write the equation and then indicate the heat of reaction delta H as being negative, since the potential energy of the products falls below the zero potential energy level. However, in the case of endothermic reactions, like the thermal decomposition of calcium carbonate into the product calcium oxide and carbon dioxide gas, the drop in the potential energy during the decomposition of the activated complex into products is less than the activation energy. The difference, delta H, the heat of reaction, is stored as potential energy in the bonds of the newly formed products. Since the average kinetic energy of the particles of the products is less than the average kinetic energy of the particles of the reactants, the system will cool down, since temperature is directly proportional to the average kinetic energy of the particles of the system. Therefore, in order to sustain any endothermic reaction, we must continually add energy to the system. In other words, the system absorbs energy.
And conversely, sir, if we come across an equation of a reaction, how will we know that the reaction is endothermic?
There are two ways of writing endothermic reactions. We can either write the heat added as one of the reactants, or we can simply write the equation and then show the heat of reaction delta H as being positive, since the potential energy of the products rises above the zero potential energy level on the curve. I want you now to attend to worksheet 401.3 in your workbook. Stop your videotape now.